Well, welcome, ladies and gentlemen, to chapter number 4. Today, our focus is going to be on chemical bonding, and primarily our focus is going to be on the ionic model. So we've spent a lot of time in some of the previous chapters talking a lot about elements and the individual components that make up elements, those subatomic particles, how those subatomic particles can change based off of the element we're looking at, whether we're looking at different isotopes, potentially whether we're looking at ions. What we're really going to focus on today is how those individual elements, those individual Legos that we've talked about previously, are put together in a certain way in order to make a variety of different compounds. And there's two primary ways that chemicals bond. One is through the ionic bonding model, which is something that we are going to talk about today. And the other is the covalent bonding model, which we will focus on in another lesson. Now, we'll talk a little bit about both here, but our primary focus is going to be on ionic bonding. Now, when chemicals bond with each other, they end up with a variety of different names based off of the types of elements that bond together, the number of those constituent elements that bond together. And so we're going to primarily focus on nomenclature as well as understand how electron movement helps us understand how chemicals bond together and the relative number of atoms that bond together. So it's a very exciting lesson. It really boils down to the fundamentals of chemistry, being able to name chemical compounds and understand how the number of atoms in each chemical compound are represented by the number of valence electrons each element has. It's a very, very exciting lesson. I'm looking forward to it, and I hope you are as well. As always, we are going to go ahead and start with the learning objectives for this particular lesson, so bear with me as we work through the type of materials that we are going to learn today. First thing we're going to do is define the term chemical bond and understand how electron behavior allows us to distinguish between ionic and covalent bonding models. We're going to be able to determine the number of valence electrons present based off of the periodic table positions, and given the number of valence electrons, write a Lewis model for an element. We should be able to state the octet rule. Remember, oct means 8, and the basis for this rule, and define the term ion. Understand how we denote ions and write chemical symbols for them. Determine the sign and magnitude of charge of an ion. Use the Lewis structure to describe bonding in simple ionic compounds. Write the chemical formula for an ionic compound given the identity and charge of the ions present. We should be able to understand the structural characteristics of ionic compounds, including the concept of the formula unit. Based on the chemical formula, recognize whether a compound is ionic or not. Give the formula for an ionic compound and recognize names and compounds of common polyatomic ions. So we have a lot we're going to get through today. Very, very excited to do so. So let's go ahead and get started. So atoms in and of themselves are not very stable in their free state. It's very difficult to go and just find a chunk of magnesium or a chunk of lithium or a chunk of gold or iron or whatever just hanging out in the ground. And so what ends up happening is that atoms tend to join or bond to other atoms in order to stabilize. Now, we'll talk more about what it means in terms of stabilization and how that works here in just a moment. But for most atoms, the way in which they bond is going to be dependent upon the number of outermost or valence electrons that are found in their structure. We talked a little bit previously about the octet rule, that is that most elements want to have 8 electrons in their outermost shell, and so there's really two primary ways that that is done. Either one atom donates its electrons to another in order for both to achieve 8, or they end up sharing pairs of electrons in order to achieve 8 valence electrons. So those two types of compounds that are going to be discussed based off of their ability to bond. And the first is an ionic compound. Ionic compounds have very, very high melting points, anywhere between 500 degrees Celsius to 2000 degrees Celsius and even higher. So they typically tend to be solids at room temperature. In addition to that, they are good conductors of electricity when they are in a liquid state or dissolved in water. However, they are not good conductors of electricity as a solid. And typically you'll find that ionic compounds are metals plus nonmetals. So notice the examples down below. You have Na and Cl. Na, sodium, is a metal and chlorine is a nonmetal. Calcium is a metal, chlorine is a nonmetal. Calcium is a metal, oxygen is a nonmetal. And notice the structure on the right-hand side. They form what are called crystalline structures. You notice that it's very much crystallized, it's very organized, it's very patterned. And you see this in things like table salt and rock salt and things like that. You see this pattern, and that's due to the fact that those materials exist in regards to ionic bonding principles. Now, ionic compounds do not have molecules as a structural unit. What you end up seeing is repeating positive and negative ions that are attached to each other. One of the most fundamental concepts related to chemistry and understanding how chemical compounds work and even breaking it down even further into the fundamental concepts of protons, neutrons, and electrons, is this idea of Coulomb's law. And Coulomb's law is something that you're probably already aware of. You just may not be aware that you know it. It's the concept that opposite charges attract one another. That is, something that is positively charged is going to be attracted to something that is negatively charged. Similar charges will repel one another, and opposite charges will attract one another. The magnitude or the size of the charges determines the strength of the charge as well. So, for example, if I have two really strong magnets that are oppositely charged, they're going to be more attracted to each other than two magnets that are relatively weak to each other. You'll see more on this here in just a moment. But the formula, the chemical formula for this that we're going to take a look at here in just a little bit, is the lowest whole number ratio of atoms within the compound. So you notice the structure here has hundreds of positive and negative ions. But notice that they all relate to each other in a one-to-one ratio. So when we describe the compound in a chemical formula, the number of atoms are going to be in a one-to-one ratio. And again, you'll see that when we do our nomenclature work here in just a little bit. Now, molecular compounds are a little bit different. They have relatively low melting points. They tend to be poor conductors of electricity and are typically a gas or liquid at room temperature. These are typically all non-metal compounds, these all contain non-metal elements. So these are things to the right-hand side of the stair step. So things like CO2, H2O, SF6. These are all things that have low melting points. They don't conduct electricity well and are typically a solid or gas at room temperature. We'll discuss more on molecular compounds in a later unit. Now, one of the key ways that we differentiate between the two different categories of compounds is because they chemically bond in two completely different ways. Ionic substances contain ionic bonds, and these are attractive forces due to the transfer of electrons from one atom to another. An ionic compound is one which contains ionic bonds, so you notice that you have two atoms that are on the right-hand side. You have one atom that is a metal that has one electron in its outermost shell, and you have atom 2, which has 7 electrons in its outermost shell. So atom number 1 is going to donate its outermost electron to atom number 2, thus resulting in both having 8 electrons in their outer shell. We'll discuss that in a moment. But the idea here is that if A loses an electron, it drops a negative charge. And if it drops a negative charge, remember that neutral atoms have the same number of positive and negative charges associated with them. So if I lose a negatively charged particle, that all of a sudden makes the atom positively charged. And because B gains an electron, it increases its negative charge, thus making it negative. And so we have a positive ion next to a negative ion. Opposite charges attract due to Coulomb's law, and you all of a sudden have something that chemically bonds with each other. Molecular compounds do something a little bit different. They contain covalent bonds. Covalent bonds are a type of attraction involving the sharing of 2 or more electrons. Now, we won't get into too much detail here, but if I do look at the example on the right-hand side, we have 2 atoms each with 7 valence electrons. So donating 1 electron to another is not going to allow each to have 8. However, if they each share 1 electron with each other, all of a sudden they now have 8 valence electrons in their outermost shells and therefore are chemically bonded together. They're going to be very stable. We're going to discuss these a little bit later in a more detailed discussion in unit number 5, but I do want you to keep in mind that no bond is truly 100% covalent or ionic. We typically put these two things into buckets because it's much easier for students to comprehend and for people to understand. There really is more of a continuum in regards to whether something is ionically bonded, covalently bonded, etc. It's a discussion for a later day, but it does make it easier for us to categorize bonding. That way we can describe it in a little more detail and provide just a little more categorization. As humans, we like to categorize things into buckets. It just makes it easier for us to comprehend that information. So take a few moments, think about what we've discussed here, and think about electron transfer versus electron sharing. Is that ionic? Is that covalent? And then provide 3 characteristics for an ionic compound and 3 characteristics for a covalent one. We'll be back and finish up this discussion here in just a moment. All right, so if we're looking at electron transfer, that is ionic bonding, and electron sharing is covalent bonding. Simple enough, we just discussed that. 3 characteristics of an ionic compound versus 3 characteristics of a covalent compound. There's a lot of things that you could put forth here, but ionic compounds are solid at room temperature. They have high melting points and can conduct electricity when a liquid or in solution. Covalent compounds have low melting points, cannot conduct electricity, and are a liquid or gas at room temperature. There's a variety of other physical and chemical characteristics that we can use to describe things that are ionically or covalently bonded, but these are the primary ones that I want you to be able to know. So let's discuss a little bit more about how valence electrons play a role in bonding in and of itself. And don't forget that the outermost electrons, or valence electrons, are the ones that are involved in chemical bonding. Now this can be a bit complex, but there's a shortened system that's shown in the diagram on the right-hand side here. The number of valence electrons is actually the same as the representative elements group number. So if I go and look at my periodic table, everything in group 1A is going to have one valence electron. Everything in group 2A is going to have two valence electrons. Everything in group 3A will have three valence electrons, 4A, 4, and etc. The only exception is helium, and that has to do with the fact that in the first energy level, there are only a maximum of two valence electrons that something can have. So helium, notice it only has two in its outer shell. Hydrogen and helium play by a little bit of a different rule. We talked a little bit about the octet rule previously, meaning that things want to have 8 valence electrons in their outermost shell, but hydrogen and helium are a little bit different. They only want 2 valence electrons in their outermost shell. So as you notice here, much like many of the things that we've previously discussed on the periodic table, is that the number of valence electrons that are present is a periodic trend. It is based off of the group number that is on the periodic table. And so if we understand and know the group number, we can very easily determine the number of valence electrons that each of these elements has on their own. So just as we discussed before, go ahead and pause the video, and all I want you to do is to write out the number of valence electrons that are present in the following. Take a moment and we will come back and discuss this here in just a moment. So simply put, all I'm asking you to do is to determine the number of valence electrons that are here, and to do that, we just need to figure out what group it's in. So calcium is in the second group on the periodic table. It has 2 valence electrons. Chlorine is in the 7th group. It has 7. Xenon is in the last group, the noble gas group. It has 8. And arsenic is going to have 5 because it is in the 5A group on the periodic table. So pretty straightforward to go through and figure those out. But how does this play a role in how we determine whether things bond or not? Well, let's take a look. So the first thing we're going to do is we're going to start drawing Lewis symbols, and Lewis symbols are just a way to represent valence electrons and how they're either donated or shared when they go through and form chemical bonds. So we're going to take a step back from that. Rather than drawing out compounds and molecules and things like that, I just want us to simply be able to draw the elements and the number of electrons that are present. And this is actually quite easy to do. In order to start this off, we're just going to write out the chemical symbol. And then we're going to add a dot surrounding the chemical symbol for each valence electron that is present. So for example, calcium has 2 valence electrons that are here. We add 1 dot on each side of the symbol before doubling up. So remember, things can have a maximum of 8 valence electrons. So if we start off with 2, we start off at the top and work towards the right. As I look at the ones down at the bottom here, I tend to prefer the symbol that's on the far left, if I'm perfectly honest with you. And the reason for that is it starts at 12 o'clock and kind of works its way clockwise, and then if need be, we double up. So you can actually have 2 electrons with each cardinal point adding up to a total of 8 valence electrons. So if I were to do xenon, for example, I'd start at the very top and I'd go from 12 o'clock to 3 o'clock to 6 to 9, then back to 12, 3, 6, 9, and thus providing 8 valence electrons that are here. So what I'm going to have you do next is I'm going to have you go through and do that here. I want you to write out the Lewis symbols for the following individual elements. I'm going to do this with you here in just a moment, so stay tuned and I will show you exactly what I'm looking for. Try these out and we'll see you in just a moment. All right, so now that you've gone through and paused the video, we're going to go ahead and write out some Lewis structures for these particular elements. So the first one we're going to do is barium here. If I find barium's location on the periodic table, I find that it has 2 valence electrons, so write out our chemical symbol, Ba, and 2 dots. Just as simple as that, folks. Let's do hydrogen. Again, first group on the periodic table, so give it a dot. Silicon. 4th group on the periodic table, so we're going to give it 4 dots. Chlorine. Group 7 on the periodic table, so let's give it 7 dots. So notice how I went back and I doubled up. Makes it look really nice and neat. And then lastly, neon is going to have 8 dots because it's in that noble gas group. Again, looks really nice and neat. That's all I need you to be able to do for this. So pretty straightforward. Now we're obviously going to do more with it than this, but this is going to get you a really good start in regards to writing out structures, in regards to Lewis structures and things like that. So what we have here is just another example or a variety of examples rather of different Lewis structures of individual elements. So again, notice that the number of dots that are surrounding each individual element is directly correlated to the number of valence electrons that are present in that structure. And again, that is based off of its periodic table location. So you can see all of those there. Pretty straightforward to go through and do. I feel like we're good to move on. So when we talk about the octet rule, this can be a little bit complex, so make sure you stay with me here. Atoms of a certain number of valence electrons are most stable. Remember that we talked about noble gases being the most stable elements of all on the periodic table. Atoms that lack the most stable number of valence electrons will bond with others to obtain that stable number of valence electrons. So atoms are going to do one of two things. They're either going to donate electrons or take them in order to achieve 8 electrons in their outermost shell, or they're going to share electrons in order to do so. Today, what we're primarily going to focus on is the donating and taking of valence electrons. The octet rule is the concept that atoms will donate, take, or share electrons from other atoms in order to get 8 valence electrons in their outermost shell. That is where they are most stable. Some people will use the term happy. Atoms don't really have feelings, so I don't prefer to use that term, but you get the idea. The only exceptions here are hydrogen and helium, which only want 2 in their outermost shell. That plays a little bit more of an important role when we draw Lewis structures for compounds, but still an important rule to know nonetheless. So remember what happens with ionic bonding. It involves the transfer of electrons between 2 or more atoms, and this involves a metal and a nonmetal. So what this means is that when electrons are transferred from one material to another, something is going to lose electron or electrons, and something is going to gain an electron or electrons. Ions is the term that we use to describe atoms with an electrical charge due to a gain or loss of electrons. If an atom gains electrons, gains negative charges, it becomes negatively charged. If an atom loses electrons, it becomes positively charged. So we need to take into consideration that proton to electron ratio, right? We can't change the number of protons. Remember, if we change the number of protons, we change the element that's on the periodic table. But we need to think about the relative number of electrons when compared to that of the number of protons. If something gains a negative charge, remember atoms are naturally neutral. So if something gains a negative charge, it will naturally have more negative charge than positive and therefore carry a negative charge. If an atom loses an electron, there's going to be more positive charge than negative charge, and so therefore it becomes positively charged. So we really need to think about these things in terms of the relative amounts of pluses or minuses that are present in the given compound. That will help us get a better understanding of what happens when these things gain or lose electrons. So if we look at an example here, we're going to look at sodium chloride as an example. Na as a neutral atom has 11 electrons and 11 protons, and chlorine as a neutral atom has 17 protons and 17 electrons. Well, in the process of ionic bonding, and we'll discuss why it only gives 1 electron in just a moment, sodium loses 1 electron while chlorine gains 1 electron. So sodium, by losing that electron, now only has 10 electrons, whereas it has 11 protons. So therefore, it has 1 more positive charge than negative charge, and so as a result, sodium will be a positive ion. Chlorine, however, has 17 electrons and 17 protons, but it gains 1 electron. So therefore, it now has 18 electrons when compared to 17 protons and is going to carry a negative charge. What do positive and negative ions do? They attract each other due to Coulomb's law. Remember, opposite charges attract one another. So keeping track of the relative number of protons and electrons is very, very important in regards to ensuring that we understand the difference between when positive ions are formed and when negative ions are formed. As I mentioned before, it is important to remember that ions adjust the number of electrons. We cannot adjust the number of protons to match the charge because that adjusts the identity of the element, and we cannot do that. The charge of the ion is dependent upon the number of electrons lost or gained. So depending upon how many electrons we've lost, we could have a net positive charge of +1 if we've lost just 1 electron, +2 if we've lost 2 electrons, +3 if we've lost 3 electrons, etc. If we've gained electrons, then we have a net negative charge, and that can be -1, 2, 3. Notations for charges are located in the top right of the symbol. So for positive ions, notice that in the top right-hand corner, we carry a 2+ charge, 1+, 3+, regardless of the charge. It is in the top right-hand corner. Many times you see this with the notation that we looked at back in unit number 3, where we looked at the atomic number on the bottom left-hand side and the mass number on the top left-hand side. And the same rule applies to negative ions. We're just going to include negative as a result of their charges. Notice that it's not like an addition where we say plus 2, plus 3. It is 2 plus, 3 plus, 2 minus, 3 minus. The 1 for 1 plus and 1 minus is implied as we go through and do this. But regardless, make sure that you keep track of the relative number of protons and electrons to determine what charge you end up having. So what we're going to do here is we're just going to take a moment. I want you to go through and give the chemical symbol for each of the following ions. Remember, we're thinking about the relative number of protons and electrons as we go through, as we take a look at these individual ions. So take a moment, and we'll come back in just a moment to wrap things up here for this particular part of the unit. So as we evaluate this here, it says an ion formed when bromine gains 1 electron. Well, if it gains an electron, it has 1 more negative than positive charge, so it's going to take a negative charge. So Br minus is what we're going to look for here. An ion formed when calcium loses 2 electrons. Remember, a neutral atom has the same number of protons and electrons. So if calcium loses 2 electrons, then we'll have 2 more protons than electrons, and therefore it's going to carry a 2 plus charge. A couple more questions here. Take a moment, and we'll come back and finish up this discussion. So I want to know whether a sodium plus ion has more protons or electrons. Well, notice it does carry a positive charge, so that tells me that it's going to have more protons than electrons. Protons carry a positive charge, electrons carry a negative. A Na plus ion indicates that it has lost an electron, so sodium ion will have 11 protons and 10 electrons. If the chemical symbol X has gained 2 electrons, what would be the correct chemical symbol? Well, if it gains 2 electrons, it's going to carry a 2 minus charge. So it shows 2 more electrons, so we have X with a 2 minus on the top right-hand side. And then a Ga3 plus ion is a gallium ion that has lost 3, gained 3 electrons, or gained 3 protons. Well, remember, we cannot change the number of protons, so that gets rid of the last answer choice here. If it's gained 3 electrons, it's going to carry a 3 minus charge, so it has to lose 3 electrons. You cannot change the number of protons because it changes the element. If we lose 3 electrons, that tells us we have 3 more protons than electrons, so it's going to be a 3 plus charge. Now, the octet rule helps us understand the charge associated with certain atoms on the periodic table. And atoms tend to either gain or lose electrons until they have the same number of electrons as the nearest noble gas. And just like in an airplane where the nearest seat may be behind you, the nearest noble gas may be behind the element that you are looking at. So for example, if I look at sodium on the periodic table, sodium's nearest noble gas, based off of its atomic number, is neon, right? Because neon has 10 protons and sodium has 11 protons. So in order to have the same number of electrons as the nearest noble gas, sodium's going to lose 1 electron, forming a positive charge, meaning that sodium has 11 protons and 10 electrons. Magnesium, much closer to neon than it is to argon, so it's going to lose 2 electrons, and aluminum loses 3. But notice as we move further right on the periodic table, things don't lose electrons, things gain electrons. So for example, chlorine is much closer to argon than it is to neon, so it's going to gain an electron. Sulfur gains 2, and phosphorus gains 3. The typical rule of thumb here is that metals tend to lose electrons, while nonmetals tend to gain them. So that's a really good way to figure out if your particular element is going to gain or lose electrons, is based off of whether it's a metal or non-metal. Now there's another way that we can go through and do this, and again, I also want to reiterate here, notice the charges on the individual ions that are present here. Na lost 1 electron, so it's a 1 plus. Mg loses 2 electrons, so it is a 2 plus. And Al loses 3 electrons, so it is a 3 plus. Chlorine gained 1 electron, so it's a 1 minus. Sulfur gains 2, so it's a 2 minus. And phosphorus gains 3, so it is a 3 minus. Well, this all has to do with the number of valence electrons that are present in an atom. And so that can be noticed or represented as a periodic trend as well that we'll take a look at in just a moment. And this slide here just reiterates the concept we just discussed. The magnesium 2 plus ion has the same number of electrons as a neon atom does, but because neon has 10 protons in the nucleus, it is neutral. Whereas Mg2 plus ion also has 10 electrons but has 12 protons, so it carries a 2 plus charge because it carries 2 more protons than electrons. Now again, the shortcut here is looking at the groups and understanding that each group contains the same number of valence electrons. So if we have our periodic table out, we can recognize that elements of similar groups are going to have similar charges because they have the same number of valence electrons, so they're going to lose the same number of valence electrons or gain them in order to make the same charges in the same group. So what that means is that everything in group 1A is going to form a 1 plus charge, 2A, 2 plus charge, 3A, 3 plus charge. And as I move down the periodic table, we're going to skip 4A for now. Most things in 5A form a 3 minus, a 2 minus for 6A, a 1 minus for our halogen group, and 0 for our noble gas group. So this makes it much, much easier to figure out the charges because it is, again, a periodic trend. It is that concept that Mendeleev put together of this periodic table, and it just so happens that it produces so many unique periodic properties. It really is an amazing thing. So determine the standard charge and write out the element symbol with the charge for the following. So again, it is periodic table based. Take a look at what you've written in the top columns of your periodic table, just like what I asked you to do. Go ahead and write those charges out based off of the group number, and then determine the charges for the following elements based on their periodic table location. Take a moment, we'll come back and discuss. So let's start off with boron. Boron is in that 3A group. It forms a 3 plus charge. Nitrogen is in that 5A group, so it forms a 3 minus charge. Calcium is in that 2A group, it forms a 2 plus charge. It is all based on its location and its group on the periodic table. If you can find that information, you get an opportunity to go through. And I guess this is a good opportunity to mention this as well, is that anytime you get an exam, anytime you get a quiz and you get a fresh periodic table, label, label, label. Label your metals and your nonmetals. Label how many valence electrons are present in each group that we've discussed, and label the charges. If you do that, it's going to make your life so much easier as you go through and work through this course, especially when we start going through and doing nomenclature. So ion formation occurs as a paired process. That is, when something loses an electron, something else by definition has to gain it. And as I mentioned before, electrons tend to be lost by metals and gained by nonmetals. So we represent the compounds through Lewis structures, a combination of Lewis symbols that represent the transfer or sharing of electrons in chemical bonding. Now we're going to eventually do this two separate ways. The first way we're going to go through and do this is through ionic bonding. So we're going to be transferring and moving electrons using arrows. Second way we're going to do this is through the sharing of electrons. Now that comes by in a little bit later unit when we start talking about the structure of molecules and things like that. So I want you to consider the formation of NaCl. Sodium forms a 1 plus ion by losing 1 electron, and chlorine forms a 1 minus ion by gaining 1 electron. So what we can do here is show the transfer of 1 electron from Na to Cl. So notice at the very beginning here, when I start off with this particular problem, I write out the Lewis structures for each individual element that's a part of the compound. So I have 1 Na and I have 1 Cl. Then notice what I do is I use an arrow to show the transfer of the electron from the metal to the nonmetal. Again, metals tend to lose electrons, nonmetals tend to gain them. When that 1 electron gets transferred over, Na then becomes a 1 positive charge. We put it in brackets and we put a positive charge on the outside. Chlorine gains that electron. Notice that it now has 8 valence electrons in its outer shell, and it has brackets around it as well and a minus charge. For things like sodium, and I know it doesn't look like it has 8 valence electrons, but the reality is once it loses that electron, it has the same electron configuration as the element before it, which is neon, which is a noble gas, which has 8 valence electrons. So even though it doesn't show it here, anything that shows no electrons outside of it, it's considered to have a full outer shell. All right, and then we have positive and negative charges for our sodium and chlorine. Remember that opposite charges attract due to Coulomb's law. We end up with our chemical compound NaCl. It's a little stormy outside. I'm not sure if you can hear that in the background, but it is thundering like crazy, and I love it. Now, ions may not always match the needs of other atoms. It's going to be dependent upon how many electrons it needs to lose in order to achieve an octet and how many electrons something else needs to gain in order to achieve an octet. So consider sodium and oxygen here. Sodium will lose 1 electron. However, oxygen wants to gain 2 in order to achieve an octet. So notice, when sodium donates its 1 electron, that sodium is fine. It's given away its electron and therefore is fully satisfied, takes a positive charge, and has the octet rule satisfied. But notice that when it donates 1 electron, oxygen goes from 6 to 7. It is not stable. So what that means is that we have to have a second sodium atom in the compound donate its electron to that oxygen. So that's where we get a variety of different chemical formulas is based off of the number of electrons that are transferred and the satisfaction of that octet rule. Because each sodium can only donate 1 electron and oxygen wants 2, it requires 2 sodiums in order to satisfy the octet rule on oxygen. So when we see this here, we draw out 2 sodium ions with positive charges. And because oxygen gained 2 electrons, it carries a 2 minus charge instead. So the number of atoms or ions that are going to be present here is going to be dependent upon how many are needed to go through and satisfy the octet rule. So let's take a look at the situation here. Why are 2 chlorine ions needed for every 1 calcium ion? Well, calcium has to donate 2 electrons. Each chlorine only needs to gain 1 electron. So calcium cannot donate both of its electrons to chlorine because that would have 9 electrons in its outer shell and not 8. But if we had 2 chlorine atoms instead of just 1, calcium can donate 1 electron to each of them. So in this instance, we need 2 chlorines and 1 calcium. Calcium donates both electrons, so as a result, it carries a 2 plus charge. Each chlorine gains 1, so therefore it has a minus 1 charge. But notice again, all the octet rules there are satisfied, and we end up with CaCl2 as our chemical formula. So the chemical formula, again, is dependent upon the valence electrons and how we can get all of the octet rules satisfied through the donation and taking of electrons. So what I'd like us to do here, pause the video. I'm going to show the formation of the following ionic compounds using Lewis dot diagrams. So again, draw out the individual elements. Think about how many electrons need to be transferred and then go through and rewrite them in the end with brackets and charges. It can be a bit tricky at first, but once you understand the flow of electrons from metals to nonmetals, this should be relatively easy. I'll show you here in just a moment. Pause the video and we'll go from there. All right, so let's evaluate each of these compounds and figure out what type of dot diagrams we're going to go through and draw. So the first one says Li3N. So we need to draw 3 lithiums. And we're going to draw 1 nitrogen. The next thing we need to do is to put out the number of valence electrons that are present. Each lithium has 1. I'm going to make those different color. Let's make those blue so they stand out a little bit more. I tried. And the nitrogen has 5. So 1, 2, 3, 4, 5. Okay. Now remember, the whole goal here is for either the metal atoms, or I should say both, for both the metal atoms to lose their electrons and for the non-metal to gain electrons, so that way the octet rules are satisfied. So lithium is going to transfer 1 electron each to nitrogen. That results in our 3 lithiums. Each carrying a positive charge, and our nitrogen having a full octet of electrons now, in brackets with a 3 minus. So again, even if you're not given the chemical formulas for this, you should be able to figure out how many electrons get transferred. Let's do calcium and sulfur here. Calcium, based on its periodic table location, has 2 valence electrons, and sulfur has 6. Calcium is going to transfer both electrons over to the sulfur. And so when we're done, calcium carries a 2 plus charge. Don't forget to include the valence electrons on the nonmetal. Going to carry a 2 minus here, and we're done. So same thing here. Notice we need 2 galliums and 3 oxygens. So a little bit trickier to do this, but again, each gallium 3 valence electrons, and each oxygen has 6. We transfer over the electrons. Remember, to show the correct number of electrons getting transferred to each atom. So oxygen only needs 2 to satisfy its octet rule. So the first 2 here go to this first oxygen. The subsequent 2 go to the next oxygen. And the last 2 go to the last oxygen here. So I'm going to abbreviate this a little bit just because I'm out of space. So again, all it is showing the relative number of electrons, how they get transferred over, and then making sure that you have the correct ratio of ions as well as you go through and figure this out. Now, in some instances, I may not give you the number of atoms that are present. You may have to figure that out. Again, you just need to think, are both octet rules satisfied? If not, do I need to add another positively charged ion? Do I need to add another negatively charged ion? Do I add another metal, non-metal? It's all about making sure that all those electrons get lost by the metal. And then once all the non-metals have gained their electrons, do they have all the octet rules satisfied? So our primary focus for the rest of this chapter is going through and understanding how we either name chemical compounds or figure out the formulas for chemical compounds. The key for ionic compounds is understanding the ratio of positive and negative ions that results in a neutral compound. I go back to the example of calcium chloride we discussed previously. Calcium has 2 valence electrons, while each chlorine only needs 1 to satisfy the octet rule. So that means when calcium and chlorine form a compound, we need 1 calcium and 2 chlorines. The 2 chlorines are needed to accept the 2 electrons from calcium, so that way all of the octet rules are satisfied. Thus, the chemical formula for this ends up being CaCl2. So it goes back to the ratio of atoms that are necessary once all the transfer of electrons have occurred to make sure that all of those octet rules are completely satisfied. Keep in mind a couple things as you go through and write some of these formulas. First thing is that positive ions are always written first. So when you're dealing with ionic compounds, they're always metal plus nonmetal. Metal tends to form positive ions, so they are going to be the ones that are first in the formula. Charges are never shown in the formula itself. So those positive and negative charges that we discussed, they're not shown in the formula. They're used as a way to figure out the ratio of atoms and ions in the compound, but they are not shown in the compound in and of themselves. And I'm going to show you a little bit of a secret method as well. You simply need to take the numerical value of the charges of each atom in the compound, cross them, and then drop them down and make them subscripts and reduce them if you can. This is much easier shown in practice, and that's exactly what I'm going to do here. Is I'm going to show you how to determine chemical formulas from the following pairs of elements. So give me just a minute and we'll be back in just a moment. So as mentioned before, we are going to go ahead and start utilizing the cross and drop method to showcase chemical formulas given pairs of elements. This is very easy to do. So I'm going to simply start off with Na and Cl. So we're just going to write them out. So Na and Cl. Okay, now what I want to do is I want to look up the representative charges that are found on the periodic table. So I find that sodium is a 1 plus and chlorine is a 1 minus. So this is where that cross and drop mentality comes into play here. So technically this is a 1 plus and this is a 1 minus. What we're going to do with those is we are going to take the numbers, so the 1 and 1, we're going to cross them and drop them and make them subscripts. Those are numbers that are going to be down here below. So this gives us Na1, Cl1. Ones are implied, so we don't need to write them as subscripts. So what I end up with is NaCl. Just like that. Cross and drop. Makes this process very, very easy. Let's do barium and fluorine. So barium is Ba and fluorine is F. Again, take a look at their respective charges on the periodic table. So barium is a 2 plus and fluorine is a 1 minus. Again, take the numbers, cross, and drop. So this is BaF2 is my chemical formula. That is a lot easier than having to go through and write out the Lewis dot diagrams and show the transfer of electrons. I mean, you get the same result, but this is incredibly easy to go through and do. And it works for pretty much any ionic compound. There's a couple that are a little bit tricky. So here we have 3 and 2. Again, same thing as what we've done before. We're going to cross and drop. So the 3 goes with the S and the 2 goes with the Al. So what we end up with is Al2S3. All right. Last couple of practice problems here. We're going to do Mg and O. So Mg, O, 2 minus and 2 plus. So same thing here, cross and drop. But what we end up with is Mg2O2. Now this is an instance where they can be reduced, okay? We want these to be in the lowest whole number ratio. So 2 and 2 can actually reduce to be 1 and 1, so this is actually just MgO. The other way you can look at this is 2 plus and 2 minus would cancel each other out, leaving us with a 2 plus and or leaving us with nothing, essentially. So we just end up 1 and 1. So that's another way that you can go through and look at this. We'll do the last one here, Na and N. Na is a 1 plus based on its periodic table location. N is a 3 minus. Cross and drop. Na, 3, N. So based off of the chemical formulas and the charges, you can very easily determine the formula for compounds. You just need to cross and drop. All right, let's move on. And because this is something that is so incredibly important, I'm actually going to have you do this again. I'm going to have you do this on your own. Take a few minutes, go through it, and then come back and we'll go through the answers. So again, we're going to use the cross and drop method. I'm going to speed up just a little bit. Cross and drop. So did you follow along with all that? Hopefully that's pretty easy to do. Again, figure out your charges, cross and drop. If they're the same charge, they end up canceling each other out. There are some instances where reduction will be possible, like if you had a 2 and a 4. That's something we'll encounter a little bit later on in this video. So hopefully that makes sense to you. We will continue moving forward the rest of ionic nomenclature. So let's go ahead and break down some of the structure of ionic solids and why they have such unique chemical properties. And the structure of ionic solids can be described as a lattice. That is, we have repeating positive and negative ions. So you see you have chloride ions here that are green and sodium ions that are gray. Remember that chloride ions are negatively charged and the sodium ions are positively charged. So we have this repeating positive and negative lattice structure, and what makes that unique is that it maximizes attraction and minimizes repulsion. You'll notice that it alternates between positive and negatives to where the negative ions are surrounded by positively charged sodium ions, and the positively charged sodium ions are surrounded by negatively charged chloride ions. And if you remember back to Coulomb's law, opposite charges attract. So what this does is it maximizes attraction and minimizes repulsion. That makes ionic solids very, very, very strong and very difficult to break apart, which explains why they tend to have such high melting points, because it requires a lot of energy to break the attraction between the positive and negative ions. A formula unit is defined as the ratio of the lowest whole number ratio of ions present in the compound. So you see we have lots of NAs and CLs, and you'd have, if you were just had a handful of salt, you'd have billions and billions and billions of sodium and chloride ions. But we don't write that in terms of the subscript. We focus on the lowest whole number ratio of ions that are present in the compound. In this instance, because we have repeating ions for every 1 Na plus, there is 1 Cl minus. So as a result, we just use the formula NaCl. Ionic solids are very, very symmetrical, and you notice it has a very orderly pattern associated with it. It has very regular shapes. If you take a look at sea salt before or other types of ionic compounds, you'll notice that the structure is very rigid, it's very uniform, it's also very beautiful to look at. Now, we'll utilize the term binary compound to describe a lot of the chemical formulas we're going to be utilizing today. Binary compounds, just as the name suggests, contain 2 different atoms. That's what the term bi means. Ionic compounds are always going to start with a metal and be bonded with a nonmetal. So you see here we have 2 ionic compounds and 2 covalent compounds. Can you identify which ones are which? The first one there, AlF3, contains a metal and a nonmetal, so that is an ionic bonded compound. And the last one, K2O, potassium is a metal bonded with oxygen, so that is an ionic compound as well. H2O and CCl4 are going to be molecular or covalent compounds because they are solely made of nonmetals. So let's go through and discuss some of the naming conventions here, and the naming rules are going to depend on what the compound starts with. I cannot reiterate enough. The naming rules are going to depend on what the compound starts with. So I would highly recommend that you get out a periodic table and you color in the elements that are listed here on your periodic table. Pick a color and go ahead and color them in and label them type 1. Type 1 elements have what are called fixed charges. These are the ones that we've discussed in class, where if we're in column 1A, everything has a 1 plus charge, column 2A, everything has a 2 plus, etc. There are a couple of elements that are not within those groups that have certain charges associated with them. So if you look at silver, zinc, and cadmium, they have 1 plus and 2 plus and 2 plus charges respectively. So those are the things that you need to keep in the back of your mind. To figure out the name of the formula, you simply take the name of the first element, whatever it is, and then take the stem of the second element, cut off the ending, and add "ide" to it. So again, this is much more easier to do, evidenced in practice, rather than just telling you about it. Something to keep in mind when we go through and do this is that subscripts are not included in the name. That's going to be based off of the charges. So we don't include numbers that tell us the number of subscripts. That's a little bit tricky because most people want to try to understand, why is there a 2 after this? Why is there a 3 after this? It has nothing to do with adding a root or a prefix associated with it, but rather it has to do with its charge. So notice the stems of the ions that are here. So if I had sodium chemically bonded with bromine, it wouldn't be sodium bromine, it would be sodium bromide. Carbide, chloride, fluoride, hydride, iodide, nitride, oxide, phosphide, sulfide. Take off the ending, add "ide," and that will tell you the name of the formula. So we're going to pause here, take a few moments, try to figure out the names of these compounds, follow the rules that we just discussed, and hopefully you don't have any difficulty with it. It's very important to get the basis of nomenclature down now, because later on, when we start combining in different types of nomenclature, because there are multiple ways to name things, being able to determine what type is super, super important. So take a moment, work through these, and we'll go through them together here in just a moment. All right, so hopefully you didn't have too many issues going through and naming these. The naming process for this is pretty straightforward to start off with. We have Mg and S here. Mg is magnesium. S is sulfur, but remember we're going to cut off the ending, so it is magnesium sulfide. Seems straightforward. Let's keep going. Ba is barium. That's what you do to dead chemists. But Cl is chlorine, but we're going to end up changing that to chloride. Again, cut off the ending and add "ide." Sr3p2. Again, do not care about the subscripts here, so this is strontium. Phosphorus, we're going to take off the ending. This is strontium phosphide. Aln, Al is aluminum. And is nitrogen, again cut off the ending, aluminum nitride. NaI, Na is sodium. I is iodine. We're changing it to iodide. BeO, Be is beryllium. Oxygen becomes beryllium oxide. So again, notice that there is a very strong trend that is associated with this. Take the first element, leave it as is, change the last part of the second part to "ide," and you're in good shape here, okay? Let's move on. All right, so this time we're going to work back and forth. So not only am I giving you the formulas and I'm asking you to figure out the name, I'm giving you the names and asking you to go backwards to formulas. So this is a little bit trickier. Again, pause the video, take a moment, go through, see what we can do with this, and we'll come back and figure it out. So for the first 5 here, we're going to do the exact same steps as we've done before. Take the name of the first element. Oxygen, change the ending to "ide." Ca is calcium. Br is bromine, change it to bromide. Al, aluminum. Cl is chlorine, change it to "ide," so chloride. Zn is zinc. S is sulfur, we change it to sulfide. Ba is barium. P is phosphorus. We change it to phosphide. All right, so the last 5 here, we're going the other direction. So it's important for us to be able to determine what types of elements we're looking at. Again, we're only focusing on binary compounds for now. So for right now, we can make some assumptions as to what elements we're looking at here. Ca, we have calcium nitride. So calcium is Ca. Now here, what we want to do, we're working backwards. So in order to figure out the formula, we need to know the charges that are associated with them. So calcium is a 2+, nitrogen 3-, and just as we mentioned before, cross and drop. So Ca3 and 2. Potassium selenide, potassium is K with a 1+. Selenium is Se with a 2-. We cross and drop. K2, Se. Gallium oxide, gallium is Ga. Oxygen is O, 3+, 2-. Again, those charges are based off of periodic table locations. So the formula here is Ga2O3. Aluminum phosphide, Al, is a 3+. Phosphorus is a 3-. Cross and drop, although in this case, 3+ and 3- will cancel. So we're just left with Alp. Beryllium fluoride. Lastly, beryllium is a 2+. Fluorine is a 1-. Again, we cross and drop here. BeF2. So the rules are very concrete. This isn't something that requires a lot of depth of knowledge, but rather just practice in regards to what do I do in each individual situation. Now, this does get a bit more complicated when we start adding in other nomenclature rules, but having the basics down is going to be so important for your success moving forward here. So take some time, work through these practice problems, practice them on your own. There's plenty of practice problems available on Canvas. Can't talk today. And practice, practice, practice. All right? We'll see you in just a moment. So as we continue to wrap things up for this unit, I want to go through a second type of nomenclature rules, and hopefully you went through and labeled your periodic table with all of the elements I asked you to color in that were all type 1. That is, the ones that had fixed charges associated with them. What we're going to look at now are all of the other metals that are on the periodic table. Remember that the type of nomenclature rules that you use is solely dependent upon what the compound starts with. So if it starts with any one of those type 1 elements that we colored in, we use the nomenclature rules we just looked at. If we're starting with an element that is not colored in, that is a metal that is not colored in, we need to use a different set of rules. And that is because the other metals that are not colored in do not have fixed charges like before. So for example, copper can have a 1+ charge, or it could have a 2+ charge. The only change here is that the charge on the metal must be included in the name of the compound using Roman numerals, but all other rules are the same. So depending upon the charge that's present, we can write copper 1 chloride, copper 2 chloride. Keep in mind, you need to make sure that you know your Roman numerals for this. I'll demonstrate that as we go through and do some practice problems in a moment. So how do we go through and determine the charge if we're not given that information? Well, we need to utilize the charges of the materials that we know to figure out the charges of the materials we don't know. We'll always know the charge on the nonmetals because they're always fixed. Metals, not necessarily the case. But we're also going to use the concept and idea that ionic compounds are neutral, meaning that whatever charges they have and the number of atoms that they have, everything has to combine to equal 0. So utilizing that information, we can figure out the variable charge on the type 2 metal that we're going to go through and look at here in just a moment. So let's go ahead and start by going from formula to name. Going from name to formula is actually quite easy because the charge of the metal is already given to us in the name based off of the Roman numeral. So starting off here, we are going to go ahead and look at AuBr. So I know that this is going to be some form of gold bromide. But what I need to know is the Roman numeral that's going to go into the middle. Remember, the Roman numeral indicates the charge on Au. And there's a couple of ways to do this. I'm going to go through a little bit more complex way, but you can probably figure out shortcuts as you work through it, and that's perfectly fine. The first way I'm going to do this is to first off, remember that all of my compounds have to equal 0. The charges of everything has to cancel out, and that's based off of the charge of the metal and the number of metal atoms. So basically this is going to equal 0, this formula here. So the number of metal atoms times its charge plus the number of non-metal atoms times its charge. So all of this combined together is going to equal 0. So I do a little bit of math here. So 0 equals the number of metals. So AU, there's one metal. The charge is what we're trying to figure out. The number of non-metals is 1, and its charge is 1 minus. Again, that is based off of periodic table location. So again, we take this information here, we find that 0 equals x plus -1. So x equals 1 plus. So the formula for this is gold 1 bromide. Okay? So if we utilize this formula, we can get it every time. Now there are shortcuts, and I'll talk about one shortcut that a lot of students will see, and I don't necessarily want you using it because it ends up leading to a lot of mistakes that people make when they go through and do this. All right, let's look at the second one here, FeCl2. So Fe is iron. I know that this is some form of iron chloride. So I'm going to use the formula we just looked at. So 0 equals the number of metal ions is 1. I don't know its charge. There are 2 chlorines, each with a 1 minus. Again, that's periodic table location based. So if I simplify this, I find that 0 equals x plus 2 minus. So x equals 2 plus. So this is iron 2 chloride. All right. Well, again, pretty straightforward to do that. Lastly here, CO2S3. Thing you need to keep in mind is that the charge is based off of a single atom of cobalt. So if we do the math like what we're doing, we'll come up with the right answer every time. But some people end up just thinking it's the total charge and end up making mistakes. So I know that this is cobalt something sulfide. Same rules we did before. So 0 equals number of cobalt atoms is 2. I don't know its charge. Plus 3 sulfurs, each with a 2 minus charge. Simplify, 0 equals 2x plus -6. We simplify, so 6 equals 2x, x equals 3. So cobalt 3 sulfide. Now the shortcut many of you may see, and it goes back to this crossing and dropping method. Well, if the charges cross and drop, can I just reverse cross and drop them like this? And that ends up telling us what the charge is. And the short answer is most of the time, yes, but not always. For example, each of the subscripts here is 1, so if you were to reverse engineer your cross and drop, you would think it's 1 and 1. But in fact, copper here is a 2 plus because oxygen is a 2 minus. So you can reverse engineer some of these, but you can't reverse engineer all of them as you go through and figure it out. All right? And again, the only time we use Roman numerals is if we start with a metal that we did not color in, a metal that is not a type 1 metal. Remember that the nomenclature rules you use are based off of the element that starts the chemical compound. I cannot stress that enough. So let's do a couple of more practice problems. Pause the video, try these on your own. We'll come back and talk about them. All right, I'm actually going to do 2 and 3 first, because these are the ones that are going to be a little bit easier. This first one here, ironically enough, is the one that's the most complicated out of the bunch. So the second one here is lead chloride. It's some form of lead chloride. I need to figure out what that Roman numeral is. Follow the same rules we did before. 0 equals, I have 1 atom of lead. I do not know its charge. I have 4 atoms of chlorine, each with a -1. So 0 equals x plus -4. So x equals 4 plus. Roman numeral here. Okay, need to make sure we know our Roman numerals. So 1 2, 3, 4. 4 is 1 before 5. That helps. 5, and then so on. I don't think we ever get past 5, but you get the idea. Next one here, SnO2. I know that this is tin something oxide. Same rules apply here. 0. We have 1 atom of tin. Do not know its charge. I have 2 atoms of oxygen, each with a 2- charge. 0 equals X plus 4-, X equals 4. There you go. So again, if you follow these steps, you're going to get it right every time. Now again, there are shortcuts to this. Some people can see this without actually having to go through and do the algebra, but I'm showing you the algebra just in case it's a little more difficult. Last one is V2O5. V is vanadium. Oxide. Math's going to be a little bit trickier here, but 0 equals 2 times X, which is our unknown. We have 5 oxygens, each 2-. So 0 equals 2X plus -10. Flip it out on the other side. 10 equals 2X. So X here equals 5. Plug that into our Roman numeral. Okay? Again, these Roman numerals, it takes some time to figure out. And again, you can reverse engineer some of these. This one you can't really reverse engineer. I put that in there for a reason. So that way you can see it works most of the time. It doesn't work all the time. So make sure if you need to follow these steps that are here, follow those steps. If not, that's fine. But just make sure you know when to and when to not include the Roman numeral. It is all based on what the element starts with. If it starts with anything that we described as type 1, it does not need a Roman numeral due to the fact that it has fixed charges. If it's any of the other metals, you need a Roman numeral with it. So again, it's all based on what the compound starts with. Okay, so now what I have for you is some mixed practice. The first thing I would do with these is identify, is it type 1 or is it type 2? So look at what it starts with. Look at what we just discussed. Look at what you've highlighted on your periodic table. That is going to tell you what steps you need to utilize in order to solve for all of these types of problems. All right, take a moment, pause the video, go through it, and I will wrap this up here in just a moment. All right, so I'm going to follow the steps exactly as I discussed. The first thing I want to do is identify type 1 or type 2. And then based off of that information, follow the nomenclature rules that we've gone through and discussed. So 1 and 2. Okay. So for these over here, because we are going from name to formula, it's very easy. If it has a Roman numeral, it's a type 2. If it doesn't, it's a type 1. So 1, 2, 1, 1, 2, 2, 1, 1. Now solving for these is easy. And even with the Roman numeral, it's not that hard. The Roman numeral tells you the charge, so we can go through and get these pretty easily. Magnesium bromide, Mg is a 2+, Br is a 1-. So this is Mg, Br2. I quickly notice I'm going to run out of room, so I'll try to fit these in as best I can. And if I need more time or need more space, I will go through and erase it. So manganese 2 oxide, so that's Mn, 2+, O is a 2-. Aluminum chloride, not too bad so far. Tin 4 oxide, so SN4+. Okay, this one's a little bit different here because when we cross and drop, we end up with SN2O4. Remember that if these are reducible, we are going to reduce them, so that's going to reduce to SnO2. Lead 2 iodide, remember the Roman numeral tells you the charge. Cross and drop, right? Goodness, I did run out of room. I'll just do that one quickly. Okay, so cross and drop, we got that pretty much down, right? It's the same with type 1 and type 2 here, but again, identifying those makes this a whole lot easier. I'm going to erase this, and then we're going to do the second half of the problems. Same steps for the rest of these. We're going to identify type 1, type 2, strontium, type 1. Again, based off of what you've written on your periodic table. Au, type 2, Cr, type 2, Ba, 1, aluminum, 1, calcium, 1, iron, and lead. Okay? If it has type 2, you have to write the charge. First one here, Sr3N2, no charge needed. Strontium nitride. Au2O, I know that this is gold oxide. Follow the steps. 2 gold atoms. I don't know its charge. One oxygen, 2 minus. Do a little bit of math there. You find that gold is a 1 plus. CrF3, I know that this is chromium fluoride. Do the math. 1 chromium atom. Don't know its charge. 3 fluorine atoms. Do know its charge. Follow the math. X is going to be 3. Okay, so I know I'm abbreviating it a little bit shorter than normal, but again, it's the same steps. It's the same steps every time. BaO, it's just barium oxide. AlN, aluminum nitride. CaS, calcium sulfide. Okay, no Roman numerals needed there because they're all type 1. The last two here, I'm going to clear a little more space. Fe2O3, I know it's going to be iron something oxide. Two irons of unknown charge plus 3 oxygens of a 2 minus charge. So what I get is 0 equals 2x plus 6 minus. Do the algebra there. 6 equals 2x. Each x is a 3. And that's what fits into the Roman numeral. Pb2O. So this is lead. We've done this one before, I think. It's lead something oxide. Again, follow the math here. 1 times x equals, plus 2 times 2 minus. So 0 equals x plus -4. So x equal to plus 4. So the tricky part's when it gets mixed. That's when things get a bit more challenging because I first need to figure out if I have a type 1 or a type 2, and then I need to figure out the individual steps I need to take in order to be able to solve for that. So taking your time and figuring out which ones are type 1 and type 2 are going to be very, very important. Again, look at what the compound starts with. Once you figure out what the compound starts with, then follow the appropriate set of rules that are necessary in order to do the nomenclature problem correctly. Let's move on. So the last couple of things we are going to look at for today are what are known as polyatomic ions. Now, everything that we've looked at so far has been a binary compound, meaning that it just contains 2 elements. There are ions that are out there. They're primarily negatively charged ions that contain more than 1 atom to form an ion. And you actually have a chart of this on the back of your periodic table. You have a list of polyatomic ions. Some have a 1 minus charge, some have a 2 minus, some have a 3 minus. There are even a couple that have a 1 plus charge. Now, polyatomic ions are not molecules themselves. They do not occur in nature by themselves, so they have to be bonded with something else in order to be considered a polyatomic ion. Everything else still applies. All the rules are exactly the same. Most carry a negative charge. You treat them just like normal ions. So look at the charges, cross them, drop them. The only thing that gets a little bit tricky is if you have multiple polyatomic ions. So take a look at some of these that are here. This is just a list of polyatomic ions that you have in your textbook. You may have some of these on your periodic table as well, but notice that there are a couple of different compounds that are here. So NO3, notice it's nitrate. The big thing I want you to notice with all of these is that they don't end in "ide." All right, all of the other compounds, all the binary compounds we looked at that just contained elements ended in "ide." When we look at polyatomic ions, we don't change any of the endings, and that's what helps us differentiate them when we reverse engineer and go from name to formula, is understand that they're not going to end in "ide." They're going to end in something else. They're typically going to end in "ate" or "ite." And if you look at the back of your periodic table, you have a ton of polyatomic ions that you can take a look at and evaluate. But notice they're made up of more than one atom, and they have a total charge. So we treat them as if they're their own individual ions. We will never change the subscripts of these. If we have multiple of them, we put them in parentheses and put the subscript on the outside of it. You'll see what I mean when we go through and do some practice problems here in just a moment. But again, recognize all of these different common polyatomic ions, and make sure you can recognize them as we go through and do some nomenclature practice. So when we do nomenclature, we're still going to need the charges to cancel out. The rules are still the same as what we've done before. We never change the subscripts of a polyatomic ion. So if we ever need more of them, we just put the polyatomic ion in parentheses and then put the number on the outside as a subscript. We keep the ending the same. We don't change it to "ide." So for example, KNO3 is potassium nitrate. NO3 is a polyatomic ion, it's nitrate. So an easy way to identify if we have a polyatomic ion in a compound is if we have more than two elements that are in the compound. So notice here we have three. We have potassium, nitrogen, and oxygen. That is indicative of a polyatomic ion present somewhere in the compound. So make sure you be familiar with your polyatomic ion sheet. Make sure you understand which ones are polyatomic ions and be able to look at compounds to be able to figure out where those polyatomic ions are and be able to do nomenclature with them. All the other rules are the same. We still need to take into account whether it's type 1 or type 2. That tells us whether we need to include a Roman numeral or not. And then look for those polyatomic ions. So this is going to be the last set of practice problems before we are done today, but I cannot reiterate the importance of making sure that you go through and practice with all of these. Mixed practice is going to be the most important thing that you do with this, because it is so important to identify when I start with type 1, type 2, and then eventually when we get to type 3. So for now, we'll do some practice together, and then I'm going to have you do the next one on your own, or feel free to pause the video now and try this out. SR here is a 2 plus, SO4 is a 2 minus. If we were to cross and drop these cancel. So this is just SR, SO4, and it does ask us to name this, so this is strontium, SO4 is sulfate. Again, notice, no Roman numeral here. That strontium determines what type we utilize, and that determines the nomenclature rules we have. Strontium is a type 1, we need no Roman numeral here. Al 3 plus and NO3 minus, cross and drop. Al, remember, we don't change the subscript here, but rather what we do is we take the NO3, we put parentheses around it, and then put the 3 on the outside. Al is a type 1, so aluminum nitrate. NH4, PO43, again we cross and drop. In parentheses, NH4, 3. PO4 on the outside because there's only one of them. Polyatomic ions will be type 1. So no Roman numerals required. They have fixed charges. That's based off of the information in your polyatomic ion sheet. So this is going to be ammonium phosphate. Also notice we didn't change the naming of the ending. So keep it the same. And again, just practice, practice, practice. All right, let's continue our work here. Determine the formulas in the following and name them. So we're going to keep doing this. So 1 plus and a 2 minus. We cross and drop, just like what we've always done. So that's Na, 2, SO4. Na is a type 1, so this is sodium. SO4, sulfate. Fe2, NO3 minus. Cross and drop, Fe in parentheses, NO3, 2. This is a type 2. So make sure that you include the charge here. Iron, 2, nitrate. 1 plus and 1 minus, they cancel. That's a type 1. So this is ammonium nitrite. Again, notice that the exact same nomenclature rules apply. We're just utilizing polyatomic ions as something a little bit different here. Let's do one more set. Again, pause the video and practice if you wish to do so. We're going to work backwards this time. So it says determine the chemical formulas of the following. So strontium phosphate. Again, nomenclature rules, type 1, type 1, type 2, and type 2, based off of what it starts with. So strontium phosphate, Sr, 2 plus, phosphate. Check your polyatomic ion sheet if you do not know it. Cross and drop. Potassium nitrate, again type 1, potassium is K. Nitrate, NO3, cross and drop. Iron 3, sulfate. Remember that the Roman numeral tells you the charge. And we cross and drop here as well. Gold 2, cyanide. Cyanide's a little bit tricky because it does end in "ide," and ides typically are just elements in and of themselves. There are a couple of polyatomic ions that end in "ide." Hydroxide is one, cyanide is one. Just pay close attention to it. Same thing, cross and drop. Okay? So take your time, practice. Goodness gracious, practice, 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 and you will get good at this, I promise. Sorting through all of this can be challenging. But again, the very first thing you need to do is identify what type you're starting with. Am I starting with type 1? Am I starting with type 2? Based off of that information, cross and drop, look at charges, look at endings of compounds. That's going to tell you what the names of these are. I can't reiterate it enough. You have to practice with this. The more you practice, the better off you're going to be. And the more mixed practice you do, the easier this is going to be in the long run. So that being said, this is all for chapter number 4. Appreciate your time. If you've really enjoyed the video or you think it's useful, leave a like. Make sure that you subscribe for more chemistry-related content, and we will see you very soon on the next video. Take care, everybody. Appreciate your time. Thank you so much, and we'll see you again very soon. Bye-bye.